Okay, we are going to discuss today what is called the Goodwin Oscillator. This is a three-component system. We have the variable x, the variable y, and z. And the evolution of this three-component system is described by this set of three differential equations. Okay, so you see that each of differential equation has a diagonal component minus b times x. This is the degradation rate of the variable x, minus b times y for the variable y, and minus b times z for the variable z. Okay, so this b is the degradation rate. For this variable is also the synthesis rate. So okay, so if we look here, we see that the differential equation for y is linear, and for z is also linear, and in this system there is only one nonlinear part, which is described by this type of Hill functions. Moreover, this system is already symmetrized and rescaled, so we have only one control parameter, which is b, the parameter b, and also we have the power p, the Hill exponent here. Okay, so this is not the most general form of the Goodwin oscillator, but for simplicity I just have one parameter b. Okay, normally you would have different degradation rate, different synthesis rate. Okay, so what is important of this system, that if we represent it, use a network representation x, y, and z, we see that x acts as an activator for the variable y, so we see it from here. Y is an activator for the variable z, we see it here, so y influences positively the synthesis of z, and z, on the contrary, is a repressor for the variable x. We see it here, 1 divided by 1 over z to the power p. Okay, so we know, it's very easy to find the fixed point of this system, right? The fixed point is symmetric, is x is equal to y is equal to z, and this is given by one specific values, and we call it xi. What is the xi? Xi is the parameter that satisfies this equation. So it's easy to realize if we plot so it's shown here in this variable, in this graph. Perhaps I hope it's not too confusing. Okay, but if we plot in horizontal axis, x is equal to y is equal to z. Okay, the function 1 plus z to the power p is this shape, and the function b times x is a straight line. Okay, so the intersection of these two is the value of xi. Okay, so this is the equation of xi, or we can invert this equation and invert it and get right. Xi to the power p is 1 over b xi minus 1. It's important that there is only one intersection, one solution of this equation. Okay, so we write the Jacobian, which we obtain by taking derivatives of these functions on the right hand side of these equations. So by taking derivative, we see that there is a minus b in the diagonal, right? These are the degradation rates. And in the off-diagonal term, this term is dependent on z, so it enters with some parameter here. Okay, and this is phi. This parameter phi is given by this derivative of these Hill functions, which I write it here, I calculate it here, but I can simplify this a bit. So I calculate this, of course, this Jacobian at the fixed point. So I have xi here, so I can simplify it, this expression, if I use here and I replace xi to the power p with this function. So I get this expression. So I have p divided by xi, and instead of xi to the power p, I use this one, and this part in the denominator gives this factor. So it's easy to see that this phi is actually of this type. It's important here is that this phi, it's a positive number in itself. Okay, but here it enters with the minus sign, so this is actually a negative term in the Jacobia, which gives rise to the negative feedback loop. So this negative term here is what we expect. This is a repressor, so z is repressing z, z is repressing x. Okay, and the other two terms are positive, p and b. All right, so we know what we have to do now. we have to look at the possible Hopf bifurcations here. So we have to solve the characteristic polynomial. The characteristic polynomial is very simple, has this shape. So there are two contributions here. The diagonal part gives lambda to the b, lambda plus b to the third, and the off diagonal part is phi multiplied b squared. Okay, so if I solve it, I have a cubic lambda. When I set this characteristic polynomial equal to 0, that gives me the 3 eigenvalues of my system. Okay, so I have a cubic, lambda to the third, a quadratic, linear, and a constant. Okay, so as in the previous videos, I call these coefficients A, I call these coefficients B, and this coefficient is a C. Okay, so I know that the negative feedback loop here can give rise to a Hopf bifurcation if in the case that A times B is equal to C. This is precisely the Hopf bifurcation point. All right, so I have to take A times B, that gives me 9B to the third cube. All right, and then I have to set it equal to C, and C is here, so it's B to the third plus phi, and instead of phi I replace this expression for phi, and this gives me this term. Okay, and a couple of steps I can solve this equation, and I find that I have a Hopf bifurcation when b times xi is equal to 1 minus 8 over p. All right, so this is my criterion for the Hopf bifurcations. B times xi depends on the value of xi and on the value of b. So by changing b, I change this parameter, and when this combination hits precisely this number, okay, then I have a Hopf bifurcation. It's a specific choice of my parameters. Okay, so first of all, I can see that, well, the only possibility, certainly if my p is small, is equal to 1, 2, 3, and so on, then this coefficient, so for p is equal to 1, is 1 minus 8, is minus 7, it's negative. Therefore, there is no Hopf bifurcation for this case. So I need a large p, I need p to be larger than 8, such that this ratio is smaller than 1, and this is in total 1 minus that is a positive number. In that case, I can have a Hopf bifurcation. So we can have a Hopf bifurcation only if p is sufficiently large in this model. This is a characteristic of this Goodwin oscillator. Okay, I will comment on this later. Okay, but we can solve and understand what happens here numerically if we make a global plot of everything what's going on. So I hope this plot is not too confusing because there are many lines, but let me show you first. I have one line here. Okay, what is this? This is 1 divided by 1 to the z over p. So again, the horizontal axis is the symmetry axis, x is equal to y is equal to z. Okay, we already established that the fixed point is given by the point where this is 0, so it's where the line b times x intersects this this hill function. Okay, so the intersection point is the values of xi is the fixed point. All right, and the horizontal line that once I have the fixed point, I can draw an horizontal line here. This dashed line is the line b. This value is exactly b times xi, right? Okay, right. Now my Hopf bifurcation takes place when this value b times xi is precisely equal to 1 minus 8 divided by p. So I can draw another horizontal line, okay, which is, I draw it here in red, and this is the line 1 minus 8 over p, and say that it takes this value. Okay, so let's keep p fixed now, and you see you can draw this line in this part of the graph where this abscissa is positive only if p is larger than 8, right? Because we see that if p is 2 or 3 or so smaller than 8, so this horizontal line is below this graph, so it will never intersect my curves here. Okay, so I write here, I indicate this horizontal line, this red horizontal line, if, well, it's there only if p is larger than 8. Okay. Therefore, when this line hits so I indicate with this this dot the point where the intersection of this red line with the heel curve. Okay. So now this curve b, this line b times x, I indicated here. If I change the slope, the b parameter, so this line changes. So if I take a smaller b, so this point is shifted here. Okay. So the Hopf bifurcation is precisely when this line, the dotted line b times xi, which I can change by moving it down, by removing b, is hitting precisely and crossing this red line. This is the Hopf bifurcation. This is the graphical representation of this equation, is when b times xi is hitting that line. Okay. So, and if I do further analysis here, I see that what happens to my eigenvalue. So I have a Hopf bifurcation. When I am above this point, okay, I have stable eigenvalues. So all the eigenvalues here have negative real parts, so my system is stable. I hit a Hopf bifurcation here, and below I have a pair of complex conjugated eigenvalues which get a positive real part. Okay, sorry, I said here, and in this region, when the intersection is above here in this region, I have only negative real parts for my eigenvalue, so the system is stable. Okay, Hopf bifurcations and two complex conjugated eigenvalues, they get a positive real part, so they become unstable. Here is the Hopf bifurcation, and once the b becomes sufficiently small here, so that you are beyond this point, there you have an oscillatory region after Hopf bifurcation region. So this is the analysis, and this is the typical analysis that one has to do to find out the Hopf bifurcation point. So you see in this three-component system we have this cubic equation, and we have the conditions a times b is equal to c that we have to solve and find out. Okay, so here we find that we cannot solve this. We will never have Hopf bifurcation unless p is larger than 8. So this p is the Hill coefficients, and such a high Hill coefficients is it's quite unrealistic for a system. So this Goodwin oscillator is it's a simple and nice model to see how in this negative feedback loop how this Hopf bifurcation arise, but it gives a parameter here that p is very large, and it's quite unrealistic. Okay, so it's not really we don't expect such a high Hill coefficients for really physical systems. Okay, but and also it's a very simple system. Is linear for most of the part. There is only one nonlinear component here. Is all the nonlinearity is in here. Okay, so it's an example which is easily solvable, but it has this unphysical feature that to have oscillations to reach a Hopf bifurcation point, I need a very large value of p, namely p larger than 8.